we go. So we're going to work on finding area under the curve. Okay? Now, we can't always have nice geometry. Like if we have a straight line, all lines are straight, excuse me. If we have a line, it's pretty easy to use geometry to figure out the area under the curve from the line back to the x-axis. Now, when we have polynomials or trig functions or really anything besides a line or a circle, we can't use basic geometry to help us find the exact area, but we can use geometry to help us find an approximate area under the curve, which is what we're going to do today. So today we're going to work with rectangles. Tuesday, which is the next time I will see you, because we're on school Monday, we'll work with trapezoids. Okay? No. Okay? So there's going to be 3 different ways today, and then one on Thursday, or Tuesday. There's going to be 3 different ways we're going to calculate the area. We're either going to use right-hand rectangles, left-hand rectangles, or midpoint rectangles. Now, I want to show you this cool. Okay, so here we go. Here is what it looks like for right-hand rectangles, and these are left-hand rectangles. These are right-hand rectangles. These are midpoint rectangles. Okay, now I'm going to go back to this left-hand one. What happens as we increase the number of rectangles? Okay, our area gets more accurate, correct? The fewer we have,
the less accurate you are.
The least accurate we're going to be. Okay, so keep that in mind as we're going through this. The more rectangles we have, the better, but we may not want to calculate 49 rectangles by hand, right? Okay. Don't get too ahead of me. Okay, so let's go back to this. Okay, I am actually going to give you, well, it's a part of our notes. Okay, I'm going to give you a foldable. Okay, I'm trying something new. Okay, but before I hand out the foldable, I want you to copy down these instructions. This is what we're going to do to find the area. We're going to decide how many subdivisions to use, which means how many rectangles are we going to use. Sometimes, well, it's going to be given to you, okay? But we know the more the better in a feasible manner. We're going to decide if we're going to use left, right, or middle points. That's also going to be given to you. We're going to have to calculate the width of our rectangles. Now I will tell you, for the most part, these are going to be consistent. For what we're going to do today, they're going to be consistent. We're going to need to calculate the heights. Our function is going to help us do that. And then we have to add up all of our areas. So I'll let you finish copying down my instructions. And I'm going to hand these out. Okay, so our widths of our rectangles are going to lie on the x-axis, and our heights are going to be what is touching our curve, okay? So if it's a left endpoint, then the left side of our rectangle is touching the curve. If it's a right endpoint, the right end of our rectangle is touching the curve. And we're going to go through examples using this foldable, okay? So the first thing I need you to do with your foldable is you need to take it and you need to fold it along this line so that the pictures appear in front of you. Okay? So I'll turn on the light so you can see that line better. It's not completely in half. Don't just fold it in half. What? Yes. So the pictures are going to appear next to where it says area approximate. Okay. Then what you're going to do is you're going to cut flat. So only, okay, you don't want to cut across the entire line, just where the picture is, so that you could like open it up and read the words like a little book. You may want to like open it up and cut along the lines.
Are these graphs upside down?
No, they're not.
No, they're gonna be. Are the words right side up? Okay, then okay.
I'm just saying, because they're an area under the curve, so it wouldn't be graph maybe.
That's a good point.
Okay, so the area under the curve means we're finding the area from the curve back to the x-axis. Okay, when you're done with the scissors, you can bring them back up here into Miss Cronky's box of scissors. Yep.
What if you have to run? I am doing. If you have to run different.
Wait, we gotta cut twice as fast. Yeah, we gotta cut.
I think.
We'll talk about that.
I mean, am I doing like a? Or I just.
No, when we talk about, area under a curve, if it's below the x-axis, and that's something that we'll talk about.
Like, since you might like a lack of area.
No,
Area around this.
Guys, go back in time before the big panic happened, and I missed.
no, you're okay. All right, so are we ready? So what I've done with this foldable, so you'll need this on Tuesday as well, because that's when we're going to do trapezoids. But what we're going to do is we're going to do an example where we draw our picture, you open it up, it's the instructions, and it's an example, okay? So as you're doing your homework, so here's your left, right, middle, trapezoid example, okay? Trapezoid will do Tuesday. So our first flap is our left endpoint, okay? So it says, in the left-hand sum, the height of the rectangle is given by the function value on the left side of the interval. Now, what we need to figure out is how many rectangles we're going to have, okay? And we're going to find that by calculating the change in x, okay? So I want this to go right underneath the instructions. Delta x equals b minus a over, what do you think?
Two.
N. So the end of your interval minus the beginning of your interval divided by how many rectangles do you want? N is how many rectangles do you want? So in this case, we have 2 minus 0, and I want to use 4 rectangles.
Why 4?
or 16, or 84 million.
Cause there's four.
Because they're gonna be nice for us to calculate in our head, okay? Because we're gonna go with a nice, easy example. So what is our change in x? 1/2. So that is going to refer to the width of our rectangles. Okay? The change in x is the width of our rectangles. Okay? Now flip back to the picture. We're gonna draw our picture. Okay? Now, conveniently, each grid mark is worth 1/2.
That's why it's convenient.
Okay. So we're gonna make rectangles on the left side of our function. Okay? So at 0, between 0 and 1/2, 0's on the left, so we use that as the height of our rectangle. So we have a rectangle with height 0. Then from 1/2 to 1, 1/2 is on the left. So that is the height of our rectangle.
I'm not getting this at all.
So 1/4 would be the height?
Wait, are you going up 1/2 or up 1/4?
I'm going over by fourths because this is labeled 0. Here's 1, here's 2.
Oh, so you're going over by half.
Because
I'm at
delta x is half.
You go up until you.
I need to calibrate this properly.
Okay.
Time out.
Lost the shade in the rectangle.
Okay, so here's this. That's a little better. I just go up to wherever the curve is. So then from 1 to 1/2, the left side would be there. And then from 1/2 to 1, 1/2 would, or 3/2 to 2, excuse me, 3/2 would be on the left side, so that is the piece that we would use for the height of our rectangle. So we are going to calculate this area. We have 4 rectangles, we need to calculate the area.
And this would just be the same as if we did on the other side. Like it doesn't matter if we did the triangle or rectangles on the left.
These are left-hand triangles. I mean, rectangles.
Yeah, but I'm just saying, like, if we did on the other side, I mean, does it matter?
Oh, yes, it would. And we'll talk about why. Okay, so now we're going to calculate the area. So open your flap. And we're going to calculate the area in that blank space. So our area underneath the curve. How do we find the area of this first rectangle? 1/2 times 0. Plus 1/2 times, what is the height of this rectangle?
1/4.
How did you get 1/4?
I looked at the graph.
Half times half.
Okay, our function is x squared. So when x is 1/2,
Oh,
okay, so I'm just going to write 1/2 squared, just so we know that's how we got it. Okay, this rectangle is 1/2 times 1 squared, because that's our function, x squared, plus 1/2 times 3/2 squared. These are the coordinates we're having to use.
And why is it squared?
Because our function is x squared. And so when x is 3/2, this coordinate is height would be 3/2 squared.
just getting like an exact.
Yes. So our area, okay, what do you notice about all of those rectangles? They have width 1/2. So we can really just write this as 1/2 times 0 plus 1/4 plus 1 plus 9/4. Okay. So if all of your widths are the same, you can just write the width once and then multiply it by the sum of your heights.
So you're saying not all of them would be the same width?
there might be like one or two random cases in the history of your calculus career where that could happen.
For what?
Where the widths wouldn't be the same. So what's our area? Because you forgot about this. 14/8 is the same as 7.
You're right, this is pretty fun.
Oh,
Like
just
it?
right, just right here.
Yeah, so there's no units.
There's 10.
What?
There's no units.
Well, you can say square units. It's fine. But I'm not worried about units right now.
How does that account for like all of blank space?
It doesn't. That's why we're approximating the area.
That's a lot of.
Now, if we did this with 8 triangles, would it be a closer approximation to the area? Rectangles. I keep saying triangles. I'm sorry. My child loves triangles right now.
Why don't we fill in those squares with triangles?
Yeah.
Yeah.
That would be even greater approximation.
Okay. What we're going to do on Tuesday is use trapezoid, which is kind of like filling this in with triangles.
Yeah, bro.
Why don't we just-
Okay, so now I want you to go to your third flap, open it up, it's a right-hand sum. When we do a right-hand sum, then the rectangles, we're going to use the right side of the interval to make the height of our rectangles, okay? So once again, we need to calculate delta x, okay? B minus A over n, okay? Where n is the number of rectangles that we are using. So in this case, B minus A is 2 minus 0, and I want to use 4 rectangles. Okay, so now we're going to go, fold it back over to our picture. The right-hand side is what we're going to use for the height. So from 0 to 1/2, 1/2 is on the right side, so that is going to give us our height. That function value is going to give us our height. Between 1/2 and 1, x is 1. That function value is going to give us the height of our rectangle. From 1/2 to 3/2, 3/2 is going to give us our height. And from 3/2 to 2, 2 is going to give us the height. So what I'm highlighting in green, okay, that's what we're hitting. We're hitting those function values to give us the height of our.
Makes them bigger.
So if you subtract the right-hand and one,
Okay, so tell me, are we over or under approximating right now?
over.
Excellent. Okay, let's go ahead and figure out what that approximation is.
If you averaged your left hand to right hand limit, would you get the actual area of the curve?
No.
You get the right-hand limit.
So let's talk about the area. The area of that first rectangle, 1/2 times 1/4. And how did you get 1/4? Okay, because that's the function value, 1/2 squared, plus 1/2 times, what's the height of the second rectangle? Plus 1/2 is our width times the height of our third rectangle. So our x value is 3/2.
9/4.
There we go. Plus 1/2 times the height of our last rectangle is
4.
4. X is 2. 2 squared is 4. X is 2. 2 squared gets us to the green dot of 4.
I was looking at this one.
Yeah, I know. That's why I'm helping out.
Thank you.
So our area, now remember, okay, I'm being kind of redundant here. We don't have to, if our width is the same, we can only need to write it once. So 1/2 times 1/4 plus 1 plus 9/4 plus 4. Which gives us an area of Try again.
11.38.
Which is 15 fourths. Okay. What flap is that supposed to be on? The third flap.
Second job.
John,
Reyes, dude.
Wow.
So you may need to make one. Okay, let's go to the second flap. We're gonna do the midpoints.
It's actually 15.
There,
Yeah. Pretty sure it's 15.
No, it's 15 fourths.
I got 30 over 4.
No, you got 30 over 8. You have 30 fourths times
Oh,
1.
I'm done.
Okay, so once again, delta x is b minus a over n, and in this case, we have 2 minus 0 over 4, which once again is 1/2. Now, when we have the midpoint, we're going to take the middle of our interval and figure out the heights. So, from 0 to 1/2, we're actually going to take the height at 1/4. From 1/2 to 1, we're actually going to take the height at 3/4. From 1 to 3/2, we're actually going to take the height at 5/4.
And how are you getting these?
How am I getting this? Yeah, somebody answered Jimmy's question.
It's for the midpoint.
Oh, the midpoint, for our midpoint area approximation.
What if we approximately midpoint?
Yeah.
Because on my sheet it seems a little bit different.
Yeah, it seems.
It seems like some of them are closer to the left side. They are in the middle.
Yeah.
At least when you draw.
Like they should be taller on
Mine aren't tall enough.
Still do.
If it's close, it's okay. All right. Let's talk about how we find the heights of these rectangles. Okay. So this first rectangle, our midpoint is what?
1/4.
1/4. Since our function is y squared, the height is 1/4 squared.
Oh, it's in the middle of.
Yes. Okay. It'll click. This second rectangle has width of 1/2 and height of whatever the function value when x is. 3/4 is the midpoint of 1/2 and 1.
Oh, okay, long term.
Okay.
Wait, can you slow down a little bit? Like, what are you doing? How are you getting the 1/4?
Okay. 1/4 is the middle of 0 and 1/2
Yeah.
because our first rectangle has length 1/2.
Oh.
Yeah, we're just finding the middle of the width.
So we're finding the middle, and then we have to evaluate the function value to get the height there. Okay? And so then our next midpoint, so between 1 and 3/2 would be x is
5.
5/4, so we have to plug that into our function to get the function value. And then our last midpoint is at
7.
7/4. Now, what do you notice about all of those midpoints? They're how much apart?
Half.
Oh my goodness, they're a half apart.
Yay.
Okay, so what we have is our width times the sum of our heights. Which from here on out, you can write it as the width times the sum of the heights. And that's what we will from here on out for the next 10 minutes.
We don't have to write that first part out.
Pretty much no.
And this is our actual.
This is still an approximate because there's a little bit above and a little bit under each of the,
84.
which is?
42 over.
Yeah, because it's X squared, but X is equal to 1/2.
Are you kidding about the 1/2?
No, I'm simplifying
So why you square it plus
No, 1/4 is, that's for
Oh, I see, I see.
in the X, yeah, you plug those
Okay.
in the X.
Are we all on the same page now?
I think so.
Okay. So now what I want to talk about is when we have under versus over approximations. Okay, so your foldables, we will do the last one on Tuesday, but I want you to keep it out to refer to it, but we're still going to take a few more notes. Okay?
Wait, I'm not done.
Oh my god, I'm so unfortunate to go.
Actually, 3 because of
I'm
homework.
still unfortunate to go.
What's that?
It's fucking.
Maybe she had to.
Josh, I
have,
can
like,
come back
2
to this,
slides of
okay?
homework.
Okay? Okay.
Oh, yes.
Anytime our rectangles are inscribed, which means they're all in our, like inside of our curve, we are under approximating. Anytime our rectangles are circumscribed, which means we're outside of the function, we are over approximating. Okay?
So these will always depend on our, if it's inscribed or circumscribed, will always depend on what of them we're using and what the interval is, right?
Something about what's happening in the interval.
Yeah.
Like what I want you to look at is your left and right pictures and that picture, those two pictures up there. Because there's something different between your pictures and those pictures.
One's left side, one's right side.
Okay. Maybe let's think of increasing versus decreasing. Right? So decreasing, these right hand rectangles are going to fit underneath, right? When it's increasing, where are your right hand rectangles? They were outside, right? They're circumscribed. Here, when we're decreasing, the left hand rectangles are circumscribed. But when we had an increasing function on your piece of paper, our rectangles were inscribed. Okay, those are things you're going to have to think about. Are my rectangles going to be inscribed or circumscribed, depending on whether we're increasing or decreasing? Okay, so I'm going to ask us to find the over and under approximation of an area. And that's our last example, split into two
Is
slides.
this without a picture though? Or is it everything?
Well, I have a picture up here, but
Like on homework?
you're going to have to think about what the graph looks like. Okay? So I want the upper and lower sums of this guy. Okay? So we're going to start with the lower. If I want the under approximation, what kind of rectangles are we going to use? Okay? So the first thing we need to calculate is delta x. Well, let's draw a picture to make sure, so that you believe me. So from 1 to 2, right? So all of the right hand. 1, 2, 3, 4. Well, it's not the perfect graph, but that's what we're calculating. Okay? So first we need the width of each of those rectangles. Nathan, please tell me how you found that.
B minus A over 5.
So 2 minus 1 over 5, so 1/5. Okay.
Oh, so N is triangles and
Okay, so get out your calculator so you can help me figure out what each of these y values are. So our 1/5 is the width for all 5 of these. So now we need the 5 different heights. If I want the height of this first rectangle, what are we going to plug into our function? 6/5. If I want the height of that first rectangle, it has the height when x is 6/5. So plug 6/5 into this and tell me what you get. Okay.
Yeah.
So each of these have width of 1/5, right? So this is when x is 1 plus a fifth, plus a fifth, plus a fifth, plus a fifth, 2. Right? And so if we're taking right hand endpoints, then on the right of the interval is what we're using for our height. See what I mean?
So you just.
Plus. Okay? Our next rectangle has height when we plug in what for x? 7/5. You know what? These are all nice decimals, aren't they?
Yeah.
Okay, let's just do decimals. That's fine. Because it's something over 25, it's going to be a nice decimal. So 4.04, the first one was 4.56. If they're not nice decimals, leave them as fractions. Okay, but these are okay decimals. They stop. Our next rectangle has height when x is 8/5. 3.4. 4. Plus, our next rectangle has height when x is 9/5. Plus, our last rectangle has height when x is, so it is 2. So we can add those up, multiply by 1/5.
This is only for the lower one, right? We should have to find out.
Right, this is our under approximation. But the next one's going to go lickety split because we've already done this one. Anybody have an answer for me?
Remember when we had a sleepover last week, I left in there?
No.
3.5.
3.36 is what I got.
I like 3.36. All right, so now we want the upper sum. So we want the over approximation, which means we're going to use left hand endpoints. Everything's the same as far as our width. We're just now creating rectangles where we use the left part of the interval. Okay? So that first rectangle is going to have height when x is 1. Okay, instead of 1/5. So when x is 1, our height is 5. Plus, our second rectangle is going to have height when x is 6/5. Plus, our next height when x is 7/5. 4.44, right? 0.04. Plus, our next height. 3.44 plus our next height, 6.76. Okay. So you should have 5 heights, and they should all be when x is 1/5 apart, because that's our width. So put down your calculators. I'll just tell you that this.
99.
Yes. 3.96. And that better be more than your lower sum, right?
Is it always gonna be like all that we do left and right and then it's only one number, but the endpoints of our right and left is gonna change?
Yes. Because if you have the same width, then only one number is gonna be different. Do you see what Zach's talking about?
Yes.
Okay. So please use that to help. Okay, now our midpoints, they're gonna be all different. It's your homework. Okay, this is actually a pretty nice assignment for a 3-day weekend. It's not too strenuous.
Wait, does it give us the graphs in the book?
You might have to picture them, and if you want to draw them, I think that is fine. But eventually you're gonna do enough of these where you're kind of be able to do it without looking at the picture. But anytime you wanna graph a picture, I'm not gonna stop you.
Yeah, yeah.
Yes.